well, if you get the wrong, that should do it. Is it like red? Yeah. Okay, so I had just a little bit left in chapter 2 to talk about. This was section 2.7 on coframes. What's that? Right. Structure equations. So yeah, what I got to last time was essentially we defined for frame, I'll just give a quick recap here. For frame E1, E2, E3, right? If omega ij of v is, covariant derivative in the v direction of ei dot ej, right? And we can write ei as equal to a, how's it go? I know this is u1. I know this is u2. And I know this is u3. I got to stop and think about what the indices of A looked like. Like E1 is the first row of A, right? Like the coordinates of E1 are the first row of A, the attitude matrix. So I should have like I1 here, I believe. I2, I3. Right? So if we define the connection coefficients, the omega ij are the connection coefficients. Actually, the connection 1 forms, right? So these guys are the connection 1 forms. The reason I say that is they're 1 forms. Let me be a little bit less silly. So here, omega ij is an element of what we'll call lambda 3, 1 rather, of R3. I haven't said that notation in class yet. 1 forms on R3. In contrast, V, a vector field, was a vector field, which I've been using this symbol for on R3. Right? But for each choice of I and j, you fix an I and j, omega ij gives us a mapping from vector fields to, well, I have to fix a point, plug in a point, right? And so, oh, curses, now instead of vector fields, I need TP R3, the vector's at a point. And so you plug in a vector at a point into this 1 form, and out pops a number. So, and it's linear, so it's a 1 form. Anyway, these are the connection coefficients, which we can identify with 1 forms. I mean, they are 1 forms. And here, this A, this is the attitude matrix, right? A so-called attitude matrix, right? And the rows in the attitude matrix are the components of the frame with respect to the Cartesian basis, right? And then the thing I proved, argued, whatever you want to say, the theorem was this. Theorem, which is that omega is equal to, what's the formula in terms of matrices of dot product, matrices of wedge products and such? It was like there's a dA and an A transpose. Which one goes first? Which one goes last? I don't remember.
Is it the V of A equals dA of B? Oh, is it dA wedge B plus negative 1p A wedge dB?
No, I'm looking for the formula omega equals something in terms of A. I think it's dA A transpose or wedge A transpose. I could be wrong about that though. This would have been proved in 2.6. Yeah. I think so.
No, it's just properties and those properties in class. Formulas of covariance derivative.
It's dA, yeah, dA wedge A transpose. This is it. I thought I derived that in the video. I mean, for what it, that's actually in section 2.7 in the book. It is, let's see here, theorem 7.3. All right. So I think my numbering of my notes versus like the section numbering of my notes versus the book is like one off. My section 2.7 corresponds to his 2.8. So. What would this wedge that? I mean, you could write it with or without the wedge here. Well, that is also true. I mean, so we have AA transpose is equal to the... Yeah.
Let A be the additive matrix of a given frame, then omega is equal to dA wedge AT.
There we go.
And then you go on to prove that. But use the covariance derivative. You set EI equal to AI1 U1 all the way up to E3.
Mm-hmm.
And then you define omega ij of B is equal to the covariance of B acting upon EI
Dot EJ. Mm-hmm.
for every B in the vector space of R3.
Right, right. So, so that's where we are, right? We have these things. And so you can build the connection coefficients from the attitude matrix. You take the interior derivative of the attitude matrix, wedge it with the transpose of the attitude matrix. That's the connection forms. And so in section 2.7, which corresponds to section 2.8 in O'Neill, we learn further things about this wild world of connection forms and so forth. And in particular, we're going to look at some formulas that arise from what's called the coframe. All right. So I talked about this a few weeks ago, I think, but we never kind of did much with it yet. Now we're going to do a little bit more with it. So if E1, E2, E3, suppose these are vector fields, right? On R3 for the sake of discussion. Then theta 1, theta 2, theta 3 is dual or coframe to the to the given frame. If theta I on EJ is equal to delta ij. So and theta I, if you fix a point, they're mapping from TPR3 to the reals, and they're linear. I could also say that if we don't fix a point, if we just let like theta I act on a vector field, I'll say, by the way, if I have theta I acting on V, then this gives me a smooth function on R3. A smooth function. So like if I feed a one form, a vector field, what I get is a smooth function. If I fix the point, if I let a one form at a point act on a vector at a point, I get a number. But because the one form and the vector fields are both smooth, when you put them together and construct a function in this way, you get a smooth function. All right, great. So the dual or the coframe. Example. If we have E1 equal to U1, E2 equal to U2, E3 equal to U3, right? Then theta 1 is dx, theta 2 is dy, and theta 3 is dz. And like generically speaking, if you look at this theta I acting on Ej, in this case, is dx upper I acting on partial xj, right? But remember what we've talked about, this is equal to partial xi, partial xj, which by the way is Kronecker delta ij. So this little calculation here shows you that the differentials are the coframe to the coordinate derivatives, right? What's the attitude matrix in this very silly case? Example continued. The attitude matrix is, well, E1 is what? Is what? It's U1, right? So if we look at E1 is equal to 1 E1 plus 0 E2, I mean 0 U2, I'll write it up here. E1 is 1 U1 plus 0 U2, right? Plus 0 U3. So that tells me the first row in the attitude matrix is 1, 0, 0. And for entirely similar reasons, the attitude matrix is 0, 0, 1 for the second row and 0, 0, 1 for the 0, 0, 1 for the third row. In other words, the attitude matrix in this case is the identity matrix. All right? So for the Cartesian matrix, Cartesian basis, the identity matrix is just the identity. The attitude matrix is just the identity matrix. And so what's dA in this case? What's the exterior derivative of a constant matrix? It's just the zero matrix. Like all the exterior derivatives are zero, so it's just zero. So in this case, what are the connection forms? dA, A transpose, right? Which in this case is 0 times I transpose, which is otherwise known as 0. So the connection forms are 0, right? And going back to, the formula for the covariant derivative is just what? Covariant derivative of W with respect to V is what? It's the sum, I equals 1 to 3, of Wi acting on V, Ui, right, plus, like, generically speaking, we get some interesting stuff over here, right? Sum over I and j of, like, how's it go? Anyway, term with, I'll just write it, term with omega, right? But this whole piece is 0 in this case, and so we drop back down to this simple formula, which I would point out, again, is really nothing more than a vector of directional derivatives. We look at the directional derivative of W1 in the v direction for the first component, the directional derivative of W2 in the direction of v for the second component, the directional derivative of W3 in the v direction for the third component. So the covariant derivative is a vector of directional derivatives. It's measuring how the vector field W is turning into the direction of v. All right. Okay, so sorry if that's a little bit of a repeat from the video, but just to try to get us all on board with what these letters mean and, you know, get it back on our system. Great. Now, so there's a theorem. If V is a vector field, right, and let's say alpha is a one form, then V is equal to the sum over I of V, well, let's say this, theta I acting on V, EI, and alpha is equal to the sum over J of alpha acting on EJ, theta J. So like this was actually, your last homework was like this, if you really look at it. So the proof here, if we take, you know, first of all, V is a vector, right? And if E1 through E1, E2, E3 is a frame, I'm assuming they're a frame throughout this lecture, okay? So I won't keep stating it, but they're a frame. And so what happens, first of all, we can write V is equal to what? Something like AU1, right? Well, let's say sum over I, or let's say J, fine. Sum over J of A upper J EJ, right? That's because E1, E2, E3 is a frame, right? Which means we can write any vector as a linear combination of the frame. So to prove this theorem, we need to show that A upper J is in fact nothing more than theta J acting on V, right? Like that's the claim of the theorem, that this coefficient is actually just that, you know, with the letter changed, of course. Fine, here I'll make them J's. Better. So all you got to do is just consider calculate, right? Calculate theta J on V. What do we get? I guess I should do theta I on V. I'm an idiot. If I could just follow my own notation for a second here. Theta I on V is what? It's theta I on the sum over J of A upper J EJ, right? But then theta is assumed to be linear on vectors, right? So I can pull the sum, I can pull the numbers out. And what do I got? I've got theta I on EJ. But what is theta I on EJ? Well, by assumption that theta is a coframe, that's Kronecker delta IJ, right? So what's that? What happens to this sum here? Everything's 0 except for where J is equal to I. So that summation reduces to just A upper I. Which is half the theorem, right? Because now I have shown that this is equal to that, which is that claim. Are we good? Okay. How about the other half of the theorem, alpha? So, continuing the proof, if alpha, let's say, is equal to the sum over I of C lower I theta upper I can do that because, well, you can prove that coframe is a frame. I won't do that in here, but you can prove that. So since I know that the coframe is a frame, I can expand the one form with coefficients, right? Like this. And then what do? Consider alpha on EJ, right? What happens when we look at alpha on EJ? What do we get? Alpha on EJ, what do I want to do? Yeah, okay, alpha on J. I get this sum, I, Ci, theta I. And how does this work? What are we looking at here? So each of the theta i's is a function, right? We're adding functions together and multiplying by numbers. How do we define sum of functions and scalar multiples of functions to act when they act on something? What's our rule in mathematics for that? We define them pointwise, right? Pointwise addition of functions, that's still in play here. And so by the definition of function addition and scalar multiplication, this is straight up the sum over I, Ci, theta I acting on Ej. But again, that is what? Kronecker delta Ij. So what happens? So that's 0 except when I is equal to j. Now j is the free variable here. It's the one that survives. And this reduces to Cj. So now we've shown that the coefficients of an arbitrary form can be obtained by evaluation on the frame basis, like this. So we've shown that this is which when you put it back up into here gives us this formula. There it is. So that was my proposition 2.73 in the notes. All right. So moving along here, if I can find my chalk again. So consider Aij. Oh man, I've neglected a mission critical formula. Curses. I mean, this is fine what we've done, but I need to make an observation. One other thing, and I think this is essentially your homework problem. Actually, if we have so in your homework, I essentially had you do this for. Well, anyway, here it is. Notice. I say theta j acting on a vector field V. I mean, maybe I already have this. This could be the theorem. Well, anyway, we'll do it. So this is theta j. I'm sorry, guys. I'm like, there's something I need to say here. I just doesn't pop into my head at the moment. But let's suppose that f is the formula, the f upper I. This is the components of v with respect to the e basis. All right. So I'm supposing that v is written like v is equal to F1, E1, F2, E2, F3, E3. You guys see what I'm saying? So if that's the case, then we have this. But this is, you can bring the sum out, bring the numbers, Fi out, and then you've got theta j acting on Ei. Again, this is Kronecker delta Ij. So what are we left with? We're left with Fj. Well, I mean, I guess the reason this seems familiar was part of the proof we just did, right? This is exactly what I just wrote over here, right? With just different letters. Okay, but one more step. Check this out. This is equal to V dot Ej. And there's the new secret sauce, if you will. So if I want, I mean, you could you could put an addition to the theorem that, by the way, if you'd rather look at it in terms of dot products rather than, coframes acting on things, this alternatively, there's a formula. This is V dot EI, right? And this over here, well, okay, I can't write that. I don't have a dot product of alpha over there, but that's V dot EI. Now, okay, so what happens when we apply this to the U1, U2, U3 case, right? We had what? Aij was, what was that equal to? So if you guys would go back over here, if you look at this, what's the formula for Aij? I mean, you're like, well, it would be what? It would be EI dot what? If I want to put a j in the second component, I should take the dot product of this equation with if you take the dot product of this equation right here with uj, that will select aij. So the formula is ei dot uj. And I'm certain that's something I pointed out in the video, but here we go. So that is a formula that we know for the attitude matrix. The attitude matrix relates the possibly non-Cartesian frame to the Cartesian frame in that way. All right. Okay, so so then what? So then I would point out the following. We have Aij equal to ei dot uj. Okay, great. But by this theorem, I could also write that as what? I could write that as by that calculation over there, I can write that as the coframe acting on V. So here, I can write that as dx j acting on EI. So what I'm using the example. So here I had theta j acting on V, you know. But if we do this equation for the Cartesian frame, this becomes dxj on V is equal to V dot uj. So like, maybe I should just write that over here. A specific instance of this looks like dxj acting on V is equal to V dot uj. If you look at this calculation in the specific instance of the Cartesian frame, we got this. Oh, you got it? Okay, cool. Okay, so I did that over here. Now what? So I'm like, okay, well, great. I say, well, if we look at the coframe, theta I, we can write that as the sum of theta I acting on uj dxj, right? I'm sorry, I lost. Hey. Yes. Sorry, the sum is over j. I is fixed here. Now, all right, so put it all together. This is what? EI. This chalk's not showing up very good. It's kind of humid in here, isn't it? So this is EI dot uj, still with a dxj over here. And finally, getting to the point of all this, this is straight up aij. So here we go. Here's the result where I was trying to claw my way towards, and I've done it in probably the most inefficient possible way today. My apologies. But here it is. So this gives us that the coframe is related to the Cartesian. So like the non-Cartesian coframe basis is related to the Cartesian. The relation between the coframe of a non-Cartesian basis and the Cartesian basis is related in the same way that the frame and the non-Cartesian frame and the Cartesian frame is related. The same coefficients, like this relation between theta I and dxj is entirely the same as the relation between EI and U1 through U3. It's the same pattern. And so that's a little bit surprising, but there it is, theorem. This is my proposition 2.7.4, which I've entitled Attitude of Coframe, and it simply says this, EI equals the sum aij uj if and only if theta I equals to the sum over j aij dxj. So that was, again, and the backdrop of the theorem is, suppose you have a frame E1 through E1, E2, E3, and you have coframe theta 1, theta 2, theta 3, well then the coframe is related to dx1, dx2, dx3 in the same way that the frame is related to partial x, partial y, partial z, if you want to go back to that notation. Okay. Oy, oy, oy. Now, at this point, we introduce yet another notation. Vector notation. In particular, we let theta be the vector of coframes, so like theta 1, theta 2, theta 3, like that. And d zeta, I can't ever do this thing worth anything in person. That guy. This is, so this is the Cartesian one. All right. Then the theorem just stated reads theta equals to a d zeta. Pick your favorite squiggle letter. Let me start calling it squiggle.
Yeah, I looked it up, so I couldn't see.
Yeah, I think it's xi, is it? I don't know. I always forget.
No, it's zeta.
Oh, the zeta. I'm not entirely sure that's zeta.
That's what it looks like.
It's zeta? Okay, well. Okay, good. Anyway, so this is very cool because once you have a formula like this, it frees you of indices, and we can start doing our matrix of forms stuff again. Right? So like, let's play. So if we know this, all right, then we can calculate d theta. And what's d theta going to be? It's the differential of a d zeta. Now, by the way, I haven't given specific instruction as to how to multiply a matrix of forms times a column of forms. But the fact of the matter is, if you just go back to the definition that was given in the previous section for like taking the wedge product of matrices of forms, the same definition applies properly interpreted. In other words, we multiply a matrix of forms times a vector of forms in the same way that we multiply a matrix of numbers times a vectors of numbers, right? With the provision that when we multiply the objects, we just keep the wedge products in order, and the numbers right along. So, but another aspect of that is, remember we proved like a product rule, and we proved that the d squared was 0. Maybe proved is too strong a word. It can be proved if you have enough time. So I'm looking at here, I've taken the exterior derivative of theta, right? See this? I'm taking an exterior derivative of theta, and that's a product, right? No, I'm talking about the properties of wedge products of matrices of forms. So like I had this rule, d of a wedge b. I said that that was dA wedge b plus minus 1 to the degree, p was it, of a db. So I'm saying that that applies here. So with that rule, this becomes dA wedge d zeta plus a wedge d zeta. But d zeta, there's almost no need to write that, right? Because d zeta is, because of the d squared equals 0 rule, 0. So we just have dA wedge d zeta. All right? And then at this point, you do something kind of tricky. Remember, we remembered at the start of this talk here that omega was dA wedge A transpose, right? So I want to rewrite this as dA wedge A transpose. So I'll just do that and put another A in here. Well, I mean, the point is I can insert a factor of I here, right? The identity matrix, like you can wedge with an identity matrix, it doesn't change anything. That's a lemma. And so I can trade that identity matrix out for A transpose, and then A wedge d zeta. And we could, because as a matter of custom, if the matrix just has numbers or functions in it, if it's a zero form matrix, a matrix of zero forms, we don't have to write the wedge. So we could write this more simply as dA A transpose, parentheses, wedged with, well, A d zeta. What is A d zeta? Well, A d zeta was theta, right? This is theta. And what's this? No, not the identity. That's omega. And so here you have the beautiful formula that d theta is omega wedge theta. This is one of the structure equations of Cartan, one of Cartan's structure equations. It's one of Cartan's structure equations. Now, of course, the other thing we could do, now that you play this game with theta, you might go, well, what happens if we do the same kind of calculation on what we learned last time with omega? What happens if we take the exterior derivative of the connection form? Right? I mean, technically speaking, this is a matrix of connection forms, but we just say connection form because we get tired of saying matrix of connection forms. All right, so let's do it. We start with d omega. That's d of what? D of dA wedge A transpose. And again, that wedge is optional. And then same thing we did last time, product rule. Of course, one of these is like stupid because it's d squared.
Did we prove in the video how d squared is 0?
You did it for a specific instance of a function with 3 variables. Homework problem. I could prove it if I had about 10 minutes. Now, the DDA is 0. This is 0. And this over here, what is that?
Is that omega?
Well,
It's the derivative of A transpose.
Well, could we change those? Could we change those to like, what if we said, well, that's dA, A transpose A, dA, put a wedge in here somewhere, I could do that, right? Because like A transpose A is the identity, so I can put that in the middle like that, right? And that's a good move to make because what do we got here? That's omega. What's this over here? So here, let me refresh our memory a little bit here. We last time we had A wedge A transpose, or if you just like, let me just skip the wedge. A transpose is equal to the identity, right? So if I exterior differentiate this product of matrix of functions, I get dA A transpose plus A dA transpose equals to d of dI, but dI is 0. So this gives me that A dA transpose is equal to minus dA A transpose. which I think is minus omega, right? Schneikes. I've made a mistake somewhere.
Now, A transpose A is equal to I, which is concurrent to A T wedge A.
I know where I made the mistake. So that, I mean, that's not wrong. What I wrote is not wrong. That is, in fact, minus omega. The mistake is already on the board. Where's the mistake here? So this was our rule, right? This is the Leibniz rule, the product rule for wedge product of matrices. Minus 1 to the p, right? P is the degree. Exactly, so that's the problem, is that dA is a matrix of one forms. So there's a minus in the product rule that we must take account of. That was supposed to be minus, which is great news because
That means ADA transpose equals DA AT.
say again, that means what? So I get one minus from this piece right here, and I get another minus from the product rule. They together work out to give me omega wedge omega. So d omega is omega wedge omega. Nope, not 0. And you're like, it's 0 because it's a wedge. That's a great question. Shouldn't that be 0? Didn't I start this whole deal with blathering on about how the wedge product of any one form with itself is 0? Except when it's a matrix of one forms. Yeah. Now that's not, we've left the. This is also Cartan structure equation. These are both Cartan structure equations. This one and that one. We have cracked open the door into a vast subject called, the exterior calculus of Cartan. It's not 0 necessarily, no. Because it's a matrix of one forms, right? So an example that I can do here without getting into trouble is, and there's a mistake or two there's like a typo or two in the notes about the polar frame. So cylindrical coordinate frame. Cylindrical coordinate frame. We have E1 is partial R, actually. E2 is 1 over R partial theta. And E3 is partial Z, actually. So in my notes I had a typo that this was I had R partial theta in my notes, I think. There's a couple of errors in the typos in this. I was looking at it yesterday while I was getting overpriced wheels put on my van. Tires put on my van. So they're my formula for E2 is slightly flawed in the fact that it's 1 over R partial theta, and I think that was maybe the only mistake. I got to super double check it, but okay, so theta 1 is dr, theta 2 is in fact d theta, and theta 3 is dz. That makes sense if you just think about how the differentials and the partial derivatives act together, right? If we think about r, theta, and z as independent variables, then totally reasonable to think that that's the coframe, right? Because, for example, what happens theta to E2? See what happens there? You get, oh, good grief. I missed something. What goes here? R d theta. R d theta. So R d theta, acting on 1 over R partial theta, ends up giving us r over r partial theta, otherwise known as 1, all is good in the world. Now, on the flip side, these can be understood in terms of like differentials of the Cartesian coordinate formulas for these cylindrical coordinates. Like you can also obtain these formulas using Calc 3 stuff. Like r, for example, r squared is x squared plus y squared, right? So that means that 2r dr is equal to 2x dx plus 2y dy. And so if you divide by 2r, you get dr is x over r dx plus y over r dy. But by the definition of cylindrical coordinates, that's cosine theta dx plus sine theta dy, right? What's that? And then by our coframe attitude matrix, right? Clearly, partial r is dual to dr, right? So it stands to reason then that E1 is also cosine theta U1 plus sine theta U2. What I'm trying to say is once you get like a little bit of this, the rest of it like builds itself through the if you believe the theorems we've derived today. If you can find a formula for the differential, it implies corresponding formulas for the other side of things. Anyway, let me not belabor this. The point is, we have these formulas, although I think I need E2. What's the formula for E2? Minus sine theta U1 plus cosine theta U2 has to be the formula. The reason I say it has to be the formula is I know it doesn't go in the z direction, and I know it has to be perpendicular to E1 because it's theta hat, essentially. So that forces me to write that down. All right. And then what's E3? It's U3, right? Okay, so all of this to say that the attitude matrix for the cylindrical coordinate frame is what? It's cosine theta, sine theta, 0, minus sine theta, cosine theta, 0, 0, 0, 1. All right? Now, let's see here. What else can we do? We can try to we can calculate d theta. What's theta here? Sorry, I'm kind of working right to left at this point. My bad. Theta is dr up here, r d theta there, and dz down here. That's my theta. And okay, so what is, does that check with a d zeta? What's d zeta mean in this context here? So dx, dy, dz, right? So in this context, that would mean d cosine theta, good grief, dr cosine theta, d of r sine theta, well, dz. And so d zeta is in fact cosine theta dr minus r sine theta d theta And we have sine theta dr plus r cosine theta d theta. And, well, dz is dz, so whatever. Check it out. Is a times theta is supposedly d zeta, right? Excuse me, I can't get my stuff straight here. Rather, a times d zeta. What's a times d zeta equal to? Okay, cosine theta, sine theta, 0, minus sine theta, cosine theta, 0, 0, 0, 1, times this one. So what happens? Does that actually square with what we found? Do we actually get theta from a d zeta? I think we do, because when you multiply, right? So that gives me like cosine squared theta dr minus r cosine d theta. Well, I can't do math. So I think the d theta terms cancel out. I end up with sine squared plus cosine squared times r on the dr term, right? So like, if you work it out, I'm pretty sure you get dr r d theta. And, well, the dz is easier to see, but you can check it. It's things canceling and cosine squared plus sine squared being 1. You mean the d thetas in the? It's because when I multiply, I'll underline. So this multiplies with that, but then let's see here. This one multiplies with that one, and I get sine cosine minus d theta times r, and I get sine cosine d theta with plus times r. Those cancel. In contrast, when I multiply this by that, I get cosine squared, and when I multiply that by that, I get sine squared. So I just get a plain sine squared plus cosine squared dr. And of course, the dz does nothing because it multiplies 0 here. Es bueno. And so to what happens when you calculate, okay, so great, that's my theta, right? What's d theta? It's 0 dr wedge d theta, right? 0. I'm going to put us out of our misery here at the moment, but I calculated A before. I mean, see, I calculated omega. So you can calculate omega from this equation in a sort of implicit fashion. It's a little bit tricky, but there's a way you could calculate omega from this if you stare at it long enough. I have some of that in the notes, but it's tricky. Of course, we can calculate omega directly from our dA wedge A transpose formula, right? And what did I find that omega was for the polar frame? Remember? It's relatively simple. It was like 0 d theta, 0 minus d theta. I can't remember. Is it exactly that?